Okay.
Okay. Good evening, Professor. This is study group 15. My name is Adekunle Salaudin, and here is my group member, Rohini and Vijay. I'll start the introduction part of this paperwork, do the introduction part, and I will allow my group member also to take over the tree search validation, and Rohini also will take the last paper of this material. Uh, so going forward, can you next it? Yeah. So for the introduction, so uh, we on of one of the major problem of the algorithm scammers that we have so far is that they take expansion of time to find the optimal solution, and therefore the algorithms are usually used for solving relatively small problems. However, most often we do not need the optimal solution, and a near optimal solution can also satisfy our real problems. So our goal here is to apply the assumptions of two-player games, to, can you next it? Next. So we're gonna be talking about the two-player games, and our goal here. Can you back it up a little bit? Can you back up? Can you back up? Yeah, back up the slide. Thank you. So our goal here is to apply the assumption of two-player games to single agent heuristic search. So far, we needed both to check how the available moves in each case of backtracking. Each move that was tried was a waste of time, and we didn't gain any information when we tried to just to like bring the idea of the two-player game into a heuristic search algorithm. So now we want to be talking about the path planning itself. So path planning is a non-deterministic polynomial time that has a hard problem with the task of finding a continuous path connecting a system from an initial to a final goal configuration. The path followed up the optimal path which will be decided based on a constraint and conditions. For example, considering the shortest path between endpoints or the minimum time to travel within any collision. So hold on, no, back it up. So multiple path planning and pathfinding algorithm exist with varied applicability determined by the system kinematics, the environment dynamics, and also robotic computational capability and sensor and other source information available. Algorithm perform and complexity trade-off also depend on the use case. So path planning algorithms are differentiated based upon available environmental knowledge. Often the environment is only partially known to the robot AV, and an effective path planning algorithm needs to satisfy four criteria. Number one, first, the motion planning technique must be capable of always finding the optimal path in realistic static environment. Second, it must be expandable to dynamic environments. And third, it must remain compatible with an enhanced it must remain compatible with and enhance the choosing self-referencing approach. And the last one is it must minimize the complexity, data storage, and computational time. So we have a different type of we have a different path planning algorithm. We have the just Dijkstra algorithm. We have the A asterisk algorithm, we have the B asterisk algorithm, we have the rapidly exploring random trace, we have the genetic algorithm, we have the Hans colony algorithm, and etc. Well, however, we'll be talking about the uh, A star algorithm. So, however, A star and A star A asterisk algorithm is a popular graph transversal path planning algorithm. A star A star A-star operates similar to like the star algorithm, except that it guides its search towards the most promising state, potential saving a significant amount of computation time. And the Bayes algorithm uses the least expensive path and expand it's using the function shown below, like the function fn with the equals the gn plus the hn, where the gn is the actual cost from node n to the initial node, and the hn is the cost of the optimal path from the target node to n. A aesthetic is most widely used for approaching a near optimal solution uh, with the available data set node. And A aesthetic is like I said, it's like the Dijkstra algorithm in that it works based on the lowest cost path tree from the initial point to the final target point. Now we will talk about the real-time A asterisk algorithm. So the goal is to reduce the execution time of A star algorithm. Method is to limit the search horizon of A star and select an action like a single move in a constant time. Uh, and also making the decision about next move in real world without a complete plan or path to reach goal state. The two stages will be making individual move decision, performing minimum search with alpha pairing, and also making a sequence of decisions to arrive at a solution, recovering from inappropriate action and avoiding loops. So far, we only found a solution for one move at a time, but not for several moves. The initial idea would be to repeat the action done for one move several times, but that leads to several problems. So the problem there during this research, during the research in the book, the problem that I find challenging is that they might want to make a move to a node that has already been visited and will be in an infinite move loop. And if we don't allow visiting in previous visit node, then we may encounter a state where we visit all the rest of the node. So due to the limited information known in each state, we want to allow backtracking in case where we want to repeat the same moves from the same state. So the solution to this problem, to the problem is that, they should allow backtracking only if the cost of returning to that point plus the estimate cost from there is less than the estimate cost from the current point. Now, real-time asterisk is an efficient algorithm for implementing the solution. So the real-time algorithm, the RTA star is the value of Fn for node n is like the same in the alpha A star algorithm, which is the Fn equals to Gn plus Hn. The difference is the Gn in the RTA is computed differently than in A asterisk. The Gn of RTA asterisk is the distance of node n from the current state and not from the initial state. So if the implementation will be stored in an open list, and for each move, we update the G value of each node in the open list relatively to the new current state. So we're going to be going into like a drawback scenario. So a serious drawback of the above algorithm is that they must search all the way to a complete solution before making a commitment to even the first move of the solution. The reason is that an optimal first move can not be guaranteed until the entire solution is found and shown to be at least as good as any other solution. So The time to make a move is linear. It's linear in the size of the open list, and it is not clear exactly how to update the G values. It is not clear how to find a path to next destination node that was chosen from the open list. But this problem can be solved in constant time per move. The solution quality versus competition is we should also consider the quality of the solution that is returned by the RTA asterisk, and this depend on the accuracy of the heuristic function and the search depth. A choice should be made between all the families of heuristic function, while some of them are more accurate but more expensive to compute, uh, while the other are less accurate but similar to compute. And there's some information here, it describes the example that we're gonna be going into, which is in an example, we start at like a node uh, A, we update the node so that now like FB equals to 1 plus 1, which is equals to 2, and the FC is gonna be, the function of C is gonna be 1 plus 2 equals to 3. So it's storing the G function continuously at every point. So for the FB, it's gonna be 1 plus 3, which is the G function of C, which is gonna be equals to 4. The problem solver goes to B because it's the minimal and update the HA equals to FC equals to 3. Then we generate nodes E and I and updates that. So for the function of E, which is gonna be the G function of D, which is Fe equals to 1 plus 4, which is 4 is the G function of D, which is equal to 5. And the Fa is gonna be 1 plus 3, which is gonna be equals to 4. And the Fi is gonna be 1 plus 5, which is gonna be equals to 6. So the problem solver in this scenario goes to A and updates FB equals to 1 plus 5 equals to 6, and so on and so forth. So as we can notice, we won't get into an infinite loop, even though we do allow backtracking, since each time we gather more information, and according to that, we decide what will be the next move. Note that the real-time A-star algorithm does not require good admissible function and will be find the solution in any case, though a good hysteric function will give better results. The RTA hysteric running time is linear in the number of moves made, and so is the size of the hash table stored. So looking at the completeness of the RTA hysteric is complete if it stands under the following restrictions. The problem space must be finite. A goal must be reachable for every state. There can't be cycle in the graph where with zero or negative cost. The heuristic values return must be finite, and the correctness in this is going to make a decision based on limited information, and therefore the quality of the decision it makes is the best relative to be part of the search space it's has been so far. So the nodes has needed to be expandable by RTA, similar to the open list in the AR stereo. The main difference is the definition of the G and the H function, and the completeness of the RTA can be proved by induction on the number of movements. So now we want to talk about the learning RTA asterisk, which is the LRT asterisk 3 set. So until now, RTA solved the problem for single trade problem. We would like now to improve the algorithm so that it will now be good also for multiple problems in trail. So the algorithm for the first for this is the same, except for one change that will make the algorithm suitable for the new problem. So an LRTA agent is guaranteed to find a goal in any finished state safely and explorable environment unlike the ASAT. However, it is not complete for infinite state space. There are cases where it can be led infinitely astray. It can explore an environment of n states in O in function of the roots, n raised power 2. Steps in the worst case, but often does much better. Note, the algorithm will store the better value of the heuristic function instead of the second best value each time. Next.
Uh, Thank you, Salahuddin.
Yeah, this will conclude my my study on the on the A-slash algorithm and the algorithm uses for the planning paths technique. Thank you. I will now hand over to my group member here, Rohini, to take over.
Thank you, Salahuddin. Till now, we have seen how the RTA works, and now let us see the how learning real-time ASH algorithm. This LRTA algorithm is a simple and elegant, and it is considered as the faster A-star algorithm based on the performance, and it also reduces the spatial complexity while searching. And this A-star algorithm is used to determine which branch of the defined path tree best achieves the desired path planning objectives. And this algorithm is well known, but it has traditionally been applied to the path planning problems only. And it has each node has a heuristic estimation H, and at every step, current node calculates the f of c. F of c is the estimated remaining travel distance if a move were to be made to the children c. And f of c equal to k of c plus h of c. K of c is nothing but the cost of the moving to the particular child, and h of c is the child heuristic estimation. And this non-improving LRTA terminates if there is no improvement in the path length. And the LRTA algorithm terminates if there is no improvement in heuristic estimation. Memory management and path tree pruning are critical for the LRTA research to perform well. As step size decreases, tree size increases rapidly. Convergence of LRTA. An important advantage of this LRTA is that because of this repetition of the problem solving train, the heuristic value becomes the exact values. We have the following advantages under a few circumstances. First one is the initial and goal state are chosen randomly. And the initial heuristic values are admissible and do not overestimate the distance to the nearest goal. Ties are broken randomly, otherwise if we find one optimal solution, we might continue finding the same one each time, but not find the other trails to the goal. And in a finite space with finite positive edge cost and non-overestimating initial heuristic values, where a goal state is reachable from every state, over repeated trials of this search, the heuristic values will eventually coverage to their exact values along with the every optimal path. Let us see about the LRTA research validation. The first graph shows the pinpoint LRTA search validation with the pinpoint sensor footprint. And the second graph shows the LRTA using the large sensor footprint. To determine the benefits of the LRTA search, a path generated by the LRTA algorithm was compared to the path found through a brute force global search based on the Dubin points. As shown in the figure A, with the pinpoint sensor footprint, the LRTA asterisk research produces roughly the same minimum length path as the brute force global search, with the path of 0% longer. And as shown in the figure B, with large sensor footprints, this LRTA asterisk research produces 33% shorter path. And path length for the LRTA and NILRTA asterisk algorithms. This above figure shows the path length performance for the two algorithms at different step sizes. The mean length increases by about 19% across the step size range, indicating that the smaller steps are the preferable. The graph above shows that the mean path length performance of NILTRA asterisk algorithm is corresponded to the LRTA algorithm. At radius 0.2, the average NILRTA path length is 3.8% longer than the LRTA algorithm. And at the radius 0.35 and above, both the lengths are same. And at radius 0.5, the algorithm searches the entire path tree instead of searching the simplified path tree. It doesn't provide a significant benefits as the step size increases. Now let us see the running time for the both algorithms. Figure A, running time of these algorithms are identified by the total number of moves from node to node at the tree search. At graph represented, the running time results for the both the algorithms in terms of node visited at various radius. At the radius 0.2, the average running time of LRTA asterisk algorithm is about 8 crore nodes, which is 10 seconds, and about 150,000 nodes for the NILTR, which is 0.3 seconds. And at the radius 0.3, the mean running time of both LRTA algorithm is reduced by the 98%, whereas the NILRTA asterisk algorithm decreases at 247%. And at radius 0.4, both algorithms perform the same. As the step size increases, the mean running time decreases from the both the algorithms. And in real time large scale applications, we can't use the single agent heuristic search algorithms because the high cost and the fact that the algorithm does not return a solution before searching the expanded tree. And RTA asterisk solves the problems of abandoning a trail to a better looking one efficient. By overcome the effects of coupling between the path segments, the LRTA and NILRTA search algorithms plan optimal or near optimal paths through multiple targets. Thank you. Now Vijay will continue with the second paper.
Okay, you can continue sharing so I can speak on the next presentation, Rohini. Okay.
Okay. Okay.
Can you go to the next slide, please?
Yes.
Hello, can you go to the next slide, please? Yeah, okay. So we're going to discuss about the second research papers, K nearest neighbor learning real-time A-star algorithm, the simple sub-goaling for real-time research time search. And it was published by Vadim and Yagnik. So then the next slide, we're going to cover on contents. We have abstract, introduction, and learning real-time A-star algorithm, and we're going to cover the conclusion. In abstract, we're going to see the advantages and disadvantages of heuristic search algorithms. So the few advantages are the heuristic search algorithms are continually constrained by the amount of planning required for each action, and these heuristic search algorithms are utilized in video games. And one of the disadvantages of heuristic search algorithms is learning approaches typically offer poor quality solutions by repeatedly revisiting the same problem statements. To overcome this disadvantage of real-time heuristic algorithms, we have learning real-time A-star algorithm, and which it attempts to avoid learning by selecting sub-goals automatically, and it has complex and memory demanding pre-computation phase where it selects the sub-goals. And next slide, we have introduction. So we're going to see about the property of real-time agents. Regardless of the size of the problem to be solved, and an agent must plan and perform actions repeatedly within a set time interval. And here the problem is searching for path between the two locations is a typical challenge in the video games. So for this, we're going to use a heuristic search algorithm update their heuristic function with the experience as a solution. The challenge is approached in fundamentally different way with real-time search. Uh, Real-time search methods compute only a few first actions for the agent to execute rather than computing a complete possible abstract answer before the first action is taken. This is commonly accomplished by executing a look-ahead search of a fixed depth around the agent's present state and selecting the next few actions using the heuristic. Uh, so we have problem with learning process. So here the agent tends to scrub the state space due to the need to fill in the heuristic depressions. Uh, s- the solution quality result is low visually. The solution is the best performance was achieved by virtually eliminating the learning process. This can be done by calculating the heuristics in relations to nearby sub goals rather than the distant targets. The heuristic functions usually elevate the uh, problem and tend to be more accurate as they approach the goal. As a result, heuristic functions closer to the target tend to be much more accurate and require little adjustment. Next, on the next slide, we're going to see about learning real-time A-star algorithm. This algorithm eliminates the learning process. In these papers, we're going to cover the following areas: pre-computing sub-goals, runtime search, k-nearest neighbor, learning real-time A-star algorithm, and evaluation. So we're going to see the pre-computing sub-goals in the next slide. So to compute the database of sub-goals, DLR learning real-time A-star algorithm first abstracts a map using the quick abstraction schema of PRPA star, PRA star. After this participation of map into regions, D learning real-time A star considers all pairs of abstract states. For each pair, it finds an optimal path between the ground level representatives of two abstract states. The memory requirements are big of v plus v2, and where v is the number of ground level states and v two is the number of abstract states at abstraction level. And in the current slide, we're going to cover runtime search. The goal is to pick k examples that are closest to the problem at hand, since it's a k nearest neighbor. Combine their pre-computed solutions and use the combination as a solution. The similarity is defined as sum of heuristic distances between S star and S prime start, and between S goal and S prime goal. So the issues here are the global goal may be hill climbing reachable from the agent's current state, and yet the agent may select a subglobal leading it away from the goal. Although the sub goal is S0 sub goal is by constructing the hill research from S prime start, it is not necessarily so from the agent's actual state S start. The third issue lies with the possible cycle. Similarity matrix is based on the octal distance. It ignores obstacles. As a result, the most similar record may end up being the other hand of an obstacle, causing the agent of to spend a lot of time working with its way around the obstacle. On the next slide, we're going to see k nearest neighbors learning real-time A-star algorithm is an additional total to so much because it finds its objects in a limited sum of time in case the map is limited, and the objective is found within the same associated component as the agent's inductory state. And on the right side, you can see the pseudocode of the k-nearest neighbor learning real-time algorithm. Uh, Here, the asymptotic memory consumption of k nearest neighbor LRTA is a big of n for sub-goal database, big of V for LRTA star heuristic, and big of N for Tabo list T. Thus, in the worst case, the agent consumes no more than a big of N plus V memory. Comparing to the standard of learning real-time A star algorithm, the overhead is big of N. So the evaluation, the two plots within the figure appears the suboptimal of ways on the right side. By operators controlled by either D learning real-time A star empty markers or K nearest neighbor learning real-time A star algorithm. The suboptimality is communicated as the rate of how much more expensive the ways are than optimal ones. This focus closer to the center of root as preferred. Okay, then here the K nearest neighbors learning real-time A star is more expensive per move due to its reachability checks, and DLRT star requires expensive amounts of memory. To summarize, we can state that K nearest neighbor learning real-time A star performs slightly worse than D learning real-time A star, while requiring considerably less memory for its sub-goals database. The trade-off is attractive for pathfinding in video games. From this figure, you can see like K nearest neighbor is more expensive per move. Okay. Conclusion: the main idea was to construct a new high performance real-time look computation suitable for pathfinding in video games by reducing the memory requirements of D learning real-time A star real-time look method. So K nearest neighbor LRTA A star may be upgradable to fully coordinate and DLRTA star runtime performance. Yeah. Okay. Thank you. Thank you all, and thank you very much, Professor, for giving this opportunity.
Thank you, Professor, for the opportunity. Thank you for the knowledge.